take this proportional counter within the lab, and this is the spectrum of the proportional counter, which you can see the muon peak, and you also see iron and zinc peak. Approximately 8,000 proportional counters have been made at the Grace 3 experiment. I will talk more detail later of the talk. The Grace 3 experiment located in Ooty at altitude of 2,200 meter. It has two major components: 400 plastic scintillators, each of is 1 meter square area with interdetail separation of 8 meter. These are spread over 25,000 square meter. And the second component is 560 meter square muon telescope, which consists of 3,712 proportional counters. The array records 3 million cosmic ray air shower events of energy in the range of TeV to PeV. The second component is the Grace 3 muon telescope. There are 4 stations you can see here. This is the inside view of one of the station, and there are 2 modules in the front, 2 modules in the back, and there are 4 layers of proportional counters. They are arranged in perpendicular direction. In between there are concrete layers. On the top we have 2.5 meter of concrete that absorbs soft component in the showers like electrons and hadrons, and that allow the muons to pass through. So, this records muons above an energy of 1 GeV and also tracks them with a direction accuracy of 4 degree. And this muon telescope records 4 billion muons per day, making it the world's most sensitive muon telescope. Here you can see the tracks of the muons in the different modules and different layers. Now, I can go to discuss the recent results from the Grace 3 experiment. First, I will discuss about cosmic ray spectrum measurements without going much detail to the analysis technique, which is very complex. So, this is the result. We measured the cosmic ray proton spectrum. You can see here, this is the energy. It has been measured from 50 TeV to 1.3 TeV. You can see here there is a spectral break around 165 TeV. Before that, it is one spectrum. After that, it is another spectrum. And if you compare the result with other experiments, so these are all from the satellite or space-based detectors, and these are the from ground-based detector. However, this is a gap region measured by Grace 3, but you can see this is what is expected, the dashed line, that is the, but however, you can clearly see there is a clear deviation from that spectrum. So, basically the observed spectral hardening, which is above 165 TeV, the challenge is a long held belief that spectrum is described by a simple power law below the knee. So, this was published in the Physical Review Letters with a title Evidence of Hardening in the Cosmic Ray Proton Spectrum at around 166 TeV observed by the Grace 3 experiment. After it was published, there is a wide coverage in the different news articles, scientific articles, and I have put some of them. It was also covered by physics world. Now, the question asked whether any other experiment has observed this new feature. I would like to discuss in the next couple of slides. There is indications of the Grace 3 kink by ISS CREAM experiment. It is a balloon burn experiment which launched at the International Space Station. You can see here, these are the measurement, but from the ISS CREAM, but with a large error bars. However, it indicates there is a spectral hardening at the similar energy observed by the Grace 3. It was reported in FJ. There is an indication of this Grace 3 kink by DAMPE, that dark matter particle explorer, which is Chinese and Italian space experiment. Recently they measured the proton spectrum. Here is a preliminary result, but however, there is a large statistical errors. And also they combined, because of lack of statistics, they combine proton and helium data, and they are seeing also a spectral hardening around the similar energy observed by grapes. And there is a Hawk experiment. It is a gamma ray detector in Mexico. They also presented their preliminary results. You can see here grapes 3 and Hawk, they are more or less matching. But however, you can see the yellow band, that is the large statistical error of the Hawk. So if they can reduce that, probably it can confirm the grapes 3 results. The Lasso Observatory, which is probably 30 times bigger than grapes, successor of so-called Tibet AS gamma, probably they are operating more or less similar range of grapes, and they are sensitive to in this energy range. Probably they can confirm the grapes 3 result. Although I mentioned the space-based detector lack of statistics, above 100 TeV. However, there are some future-based detector which are already planned. For example, HOD, again successor of DAMPE, which is 10 times more acceptance, that can go beyond 100 TeV to 1 PeV energy. And there is a excellent idea to have a permanent cosmic ray observatory on the moon. This is a artistic picture here. So let me explain what are the interpretation. There are a couple of interpretation of this new feature. For example, this is an old paper which says there are 3 component models of cosmic ray proton spectra from 10 GeV to 100 PeV. For example, one class of model which assumed SNRs terminates its effective acceleration around 50 TeV, and there is a second class of sources, presumably supernova within the local super bubbles, that accelerate cosmic rays up to rigidity of 4 PeV or up to the new regions. So then, if you see that, then you will be able to see a spectral hardening or a spectral break around 160 100 to 200 TeV, that is discovered by grapes. Then there is another set of models called GST model. So that also assumes 2 population of sources. One population of sources, presumably SNRs, that has a cutoff rigidity at 120 TeV, and the second population of sources has a cutoff rigidity at 4 PeV. So then, if you combine that, you can see a spectral break around 100 to 200 TeV. This is after our results are published. More recently, there are a couple of papers, which have appeared in the archive. For example, this paper, which says X-ray binaries, which are compact sources, black hole, compact objects. In the relativity Zs, you have acceleration of cosmic rays to higher energy. So what you can see here, one is called this is called local sources, very nearby sources, and this is the contribution from supernova remnants, and this is what the contribution from X-ray binaries. Then if you put all together, then you will see a spectral hardening around this region, and this is the grapes 3 data they have fitted. I have some time, yeah. This is another paper which appeared very recently by a Chinese group. What they say that this could be due to there could be local sources. If there are local sources, how do you know they are local sources? If there are molecular clouds, then cosmic rays interact in the in the molecular clouds that produce gamma rays. If you can detect gamma rays, then you can say there are local sources. And this is what is the model says. These are the, you can see here, these are the grapes data which has fitted with the along with the other data, assuming there are local sources, and this pretty well matches with these models. Yeah. Now I come to the discuss the another result from the grapes 3 experiment called cosmic ray anisotropy measurements, which are also very important understanding cosmic ray, cosmic ray sources. We analyzed 3.7 billion cosmic ray events spanning over 4 years of data at a median energy of 16 TeV. As you can see here, GRACE 3 is no, I don't use anything. Yeah. Okay. Okay. Yeah. You can see here, this is the map of the cosmic ray anisotropy. As is known, the cosmic rays are almost isotropic. But however, the large scale experiments with which are collecting high statistics data, they have the cosmic ray anisotropy. You can see here there are two features here, two structures A and B. In structure A, you can see a excess of cosmic rays with a magnitude of 6.5 times 10 power minus 4 with a significance of 6.8 sigma, and there is another structure, structure B, which is observed a magnitude of 4.9 times 10 power minus 4 with a significance of 4.7 sigma. These observations confirm the anisotropy observations by two other experiments called Hawk and Argo J, which was in Tibet. As you can see, the structures are very similar in all the three experiments, and if you compare the magnitude, they are more or less similar, which confirm and establish the genuineness of these structures. What are the physical origin of this small scale anisotropy, which is not yet very well known. However, there are different models. For example, there are models which say Zeminka pulsar, which is located between this structure A and structure B, that could be responsible. The magnetic field can funnel the cosmic ray particles to produce these structures, and the crab is located here. And also there are models saying it could be origin, it could be heliotail origin. These are very preliminary results which we got recently. We analyzed called large scale cosmic ray anisotropy. You can see here, these are the large scale structures. Here you can see the deficit of cosmic rays, and these are here excess regions. And if you see the dipolar, taking the L equal to 1, you can see this is the dipolar structures, deficit and the excess regions. But if you remove the low order harmonics and consider only harmonics above L equal to 3, then you can reproduce the small scale anisotropy what we have seen in the earlier. Yeah. So here is the energy dependence of the large scale anisotropy. You can see here, this is the dipolar amplitude as a function of energy. Here is the GRACE 3 data point. It is slightly off, but you can see here the anisotropy about 100 TeV there is a decrease, and again about 100 TeV there is an increase. And here you can see here, this is the phase, the direction of the anisotropy, and this also very matches with the other experiments. It seems there is a paper, parallel paper, which shows this is the local magnetic field directions, and this is the galactic center. It seems the data points, the phase of the anisotropy that directs to the direction of the local magnetic field, and this is the what we put our GRACE 3 data point, which tells that this anisotropy could be the origin produced by the local magnetic field. That means there are local sources, and you have a ordered local magnetic field that can be responsible for producing this anisotropy. Now, the last part I will talk about the upgrade of the Grace 3 experiment. This is to enhance the Grace 3 sensitivity for cosmic ray composition measurements, for detection of PEB gamma ray sources, and to enhance sensitivity for heliospheric and space weather measurements. We want to expand the muon detector to making it a double of what it is now. For that, we needed nearly 4,000 proportional counters, and we made these counters in the Grace 3 laboratory itself. They are used, the counters are used from the Kolar gold field. As you can see, they are really rusted, but you clean it to make this kind of counters. Then there are large number of stages to make these counters. We produced 10 counters per day, and it took about 1.5 years to produce 4,000 counters. And this is the view of this what you can see here. This is the existing muon telescope, and this is the top of the present muon telescope. This is on the roof side, and after we will put concrete of 1.5 meter concrete above this one. Then the detectors are below this. Here what you can see inside view of the muon detector, there are total 16 modules which are coming under the one roof, and here this is a one module. You can see electrons have been installed. We have completed 6 module installation of 6 modules. We have another 10 modules. We are hoping to complete it in next couple of months. For this, not only detectors, you make all cutting edge electronics. In fact, most of the electronics used in this, they are developed within the labs, including amplifier discriminators, TDCs, and front end electronics, and FPGA based electronics. Yeah, this is the Grace 3 team. Since the Grace 3 experiment runs 24/7, this is the dedicated team which are responsible for running it and maintenance of it and helping to collect uninterrupted high quality data. This is the Grace 3 collaboration, which is primarily India and Japan collaborations. There are 15 institutions from India, 7 from Japan, and it is a expanding collaborations. We have 5 new collaborators in the last 5 years. And these are the people, students who completed their PhDs from Grace, and in the last 2 years, in the last year 1 PhD, and this year we have 4 PhD completed from Grace 3, and these are the ongoing PhDs students. Now, I came to the summary of my talk and future outlook. Grace 3 has measured cosmic ray proton spectrum below the knee, overlapping with the direct measurements. It has observed a spectral hardening in the proton spectrum above 165 TeV. It has observed 2 small scale anisotropic structure from a new equatorial locations. In fact, there are other groups who are interested to collaborate for this particular analysis outside India. Analysis of extraction of spectrum from other elements below and above the knee are currently in progress. It has observed both small and large scale cosmic anisotropy. Upgrade of the muon telescope together with the scintillator array expansion can provide enhanced sensitivity. For cosmic ray composition and gamma ray studies. Thank you.
Thanks so much for excellent overview of results on DFT and for finishing very in time. We have plenty of time for discussion now. Questions, please.
Very basic question. Somewhere in your slide you mentioned about heliospheric results and one more results, right? Can you talk about it?
Say it again.
You talked about heliospheric results or I think.
Heliospheric result.
Can you talk more about it? Like what?
Yeah, in fact, I did not cover because that itself is a talk. Maybe I can briefly mention what are the heliospheric results. We have many heliospheric results on space weather. For example, Graves 3 discovered a transient weakening in the Earth magnetic field that was published in the PRL, and it got a significant attention during a strong solar event in June 2015. Then when the solar storm came, that interact with the Earth magnetosphere and that weakened the Earth magnetic field. And the low energy cosmic rays, we could not have come inside the Earth atmosphere. They entered in the Earth atmosphere, then increased the muon flux detected by the Graves 3 muon telescope. So that was one of the very exciting results, and it got a significant attention from the all over world. Yeah.
Wonderful talk. Thank you for sharing this update. I was just wondering whether this processing side of it is it happening near real time or it's happening on the field in the site itself, or you have to upload the data and do the inferences elsewhere?
You are asking the acceleration process?
After the data is collected by the simulation counters and other Graves 3 UT site, whether you have the data processing co-located there itself, or
You mean to say related to the solar physics or something? Or?
no, this topic is detected. Neon detected.
Sorry.
You do it in UT or in JFR?
Oh, okay. Oh, yeah. Okay. Yeah. Okay. This is the analysis being done in UT. We have a computing cluster there. Of course, it can be analyzed from anywhere. We have this Japanese group, they do from Japan, and this, yeah. Is it your question? Yeah. Yeah.
Any other question? Okay. Yeah, over there. Coming up quite late. So this spectral steepening that you showed, I noticed that one of the experiments data point actually goes up, like the blue points with a quite small error bar. So is that some anomalous measurement there which is not agreeing, or what is about those points?
Yeah, I think this is a very interesting, question. This is, there are two branches you can see here. One is going up and the other going down. So, the spectrum of the cosmic energy spectrum of cosmic rays derived using simulations, using so-called hadronic interaction models. And there's a huge uncertainty in the hadronic interaction models. So these hadronic interaction models based on the accelerated data from LSC, but before a pre-LSC, there's huge uncertainty. So if you do use a different hadronic interaction model, you'll get a different spectrum. So that was a huge uncertainty which existed. Those results are derived using hadronic interaction models. These are the pre-LSC era models. But however, there are new hadronic interaction models which are built using the post-LSC data, and then their the agreement is much better. Yeah. So it is because that uncertainty. However, thankfully to the Graves 3 overlap with the space-based detector where you do not use these hadronic interaction models. So they are excellent since the flux is matching with the direct measurement. It provides excellent calibration of our flux measurements it agrees within the 10%. But on the higher side, where you do not have a overlap, the ground-based detector measurements, you do not have overlap with the, the space-based detector, then you have still a lot of uncertainty exist. But thankfully, the large overlap with the graph 3 overlap with the space and the ground-based, then you have more confident on the results. Yeah.
Yeah, I have one more question. This is regarding the radio follow-up.
Yeah.
Is anything have been planned, or do we have any facility that has been that is existing, used up, or being planned?
Yeah. Okay. Yeah. This is a very good question. Yes. In fact, you mean to say having a radio measurement of cosmic rays? Yeah. We had the certain. Yes, exactly. We have some discussions. There are some students who have been working for the feasibility study. In fact, there are, radio technique is very well established now. You can do that, and then in the graph 3 array, it has a dense scintillator array. It can provide a trigger to the radio array, and this is the study which has been going on. There are students involved, but right now nothing is concrete. Yeah, concrete in these directions. But in the future, we would like to have a radio antenna array within the graph 3, array. Yeah.
Do you have the record available of the even time tags for public whenever there is a detection?
Right now, our data is not public. So right now, yes, it's accessible to within the collaboration, but hopefully at the moment I do not know in future, but currently the data is not public. Yeah.
Thank you.
Close the session now. 10 seconds now.
Thank you very much for finishing it on time. So we will welcome everybody for the final scientific session of the meeting. So this session is on the Best Thesis Presentation Award, the Lady Abhayankar's Best Thesis Presentation Award. We have 4 presentations today. The presentations will continue through the tea break. So participants may feel free to leave and take their tea and come in. But we would continue with the presentations. So the first presentation is by Belinda Damien. From stars to brown dwarfs, a journey through diverse star-forming worlds. So the presentation is for 20 minutes, with 5 minutes for...
Okay, how do I turn it on? It's on. Okay. And the controller is on the podium. Okay.
All the best, Belinda.
Thank you.
Hello everyone, very good morning. I'm Belinda Damien. I'm currently a postdoctoral research fellow at the University of St. Andrews, and I work with Dr. Alex Scholz. My PhD thesis was done at Christ University, Bangalore, under the supervision of Dr. Jesse Jose from IISER Tirupati and Dr. Srija Karta from Christ University. Before I begin, I would like to express my gratitude to the jury members as well as the organizers for giving me this opportunity to present my thesis work here. And as the title reads, From Stars to Brown Dwarfs, a journey through diverse star-forming worlds, my thesis mainly focused on the stellar objects towards the lower end of the mass spectrum, mainly low-mass stars and brown dwarfs. So to begin with, I'll briefly talk about these 2 objects. So yesterday we heard in detail from Manoj about how low-mass stars form, so I'm not going into the details of it, but to give a broad idea, the low-mass stars form through the gravitational collapse of the giant molecular cloud, and due to the internal turbulent fragmentation process, prestellar cores form. And these cores further gravitationally collapse, and they form the infalling material from the envelope starts forming a circumstellar disk around the central protostar, and this gradually evolves into the pre-main sequence phase. Now, the objects in each of these evolutionary stages are classified as class 0, class 1, class 2 and class 3 YSOs. And as we move down the mass spectrum, we have brown dwarfs. Now brown dwarfs are objects which are below the hydrogen burning mass limit of 0.08 solar masses, and these objects do not have the sufficient temperature in their core to ignite and sustain nuclear fusion. So their evolution, if we see, is a process of cooling wherein the luminosity decreases with age. So young star forming regions are the ideal test beds to observe and detect these objects. And their spectral type ranges from late M to LT and white dwarfs, and the temperature ranges from 3000 Kelvin to a few hundred Kelvin. Now these objects are often called as failed stars, but I would say that they are more like an unfortunate middle child of astronomy because they often get lost in the focus that's given to stars and planets. But in this presentation, I hope to convey why these objects are important to study. So to set the stage, I will first highlight the key questions that we've tried to address. Firstly, when we talk about brown dwarfs, one of the most debated topics is how do these objects form? What is the formation mechanism behind it? So there are several theories that explain this, but the two most prominent ones are, one is that they form like, one is they form like low mass stars through the gravitational collapse of the GMC, and the other is that they form like planets due to the gravitational instability of the protoplanetary disks. But it is still not clear as to which is the dominant mechanism which creates these objects, which needs to be studied. Secondly, we've tried to address the ambiguity that is associated with the substellar initial mass function. Now, initial mass function is nothing but the distribution of stellar mass of a star forming event at birth. And as you can see from this image here, following the pioneering work of Salpeter in 1955, over the years there have been various functional forms which have tried to explain the distribution towards the higher masses, and all of them are consistent with each other. But as we move towards the lower masses, mainly the substellar and planetary mass regime, they tend to diverge. So there's a lot of uncertainty that goes behind this lower end of the IMF. For instance, like what is the minimum mass for the bottom of the IMF, and if there is a minimum mass, what does that tell us about the origin of these objects? And there's a lot of challenges in addressing the lower end of the IMF, because firstly we need a deep photometric data set for these objects which are devoid of field contaminants, and secondly we need spectroscopic confirmation to confirm their nature. And also, given that the IMF is intrinsically a statistical quantity, we do need a statistically robust sample set with which we can then essentially constrain the lower end of the initial mass function. And the third question that we've tried to look at is what is the role of environment in the circumstellar disk evolution? Now we know that these disks are the reservoirs or the birth sites for planetary systems. So the time scale that it takes for the disks to evolve is directly linked to the time scale that is available for planet formation. And this cartoon depiction here shows that in a massive star forming region, which is in a high UV or feedback driven environment, the circumstellar disks are irradiated by the strong UV radiation field from a hot massive star and its vicinity, and this truncates the disk rapidly from outside in, and this interrupts the formation of giant planets in the outer disk region. This also leads to faster dispersal of the disk at a time scale which is much shorter than the time scale that a disk in a low UV environment will take. So with these objectives, we have selected 3 targets for our study. The first one is Sigma Orionis, which is a nearby young low mass star forming region. Then we have IC 1396, which is an intermediate mass environment. And finally, we have 2 clusters, IC 1848 East and West, both of which are located in a distant massive star forming environment in the W5 complex. Now all these 3 targets are diverse in terms of their different characteristics, for instance in terms of distance, in terms of stellar density and FUV luminosity. So because of this, they are an ideal target set for us to understand the role of environment. And we've used different data sets for the study in this thesis. Mainly we've used both national and international facilities. the main observations are from DOT, from the 4-meter NASA Infrared Telescope facility, and from the 10-meter class telescope GTC. And we also have data from Subaru, optical and NIR data from CFHT, and also NIR data from the 4-meter Mayan telescope new firm instrument. And these are the other archival data sets that we have used for the study. So I'll begin by talking about the work done on Sigma Orionis. Now this is a young nearby star forming region in the solar neighborhood, and it has a massive O-type star at the center of the cluster. So in the first part of the work, we've tried to identify the brown dwarfs in this region and then trace the initial mass function. Now canonically, the brown dwarf identification is done by using photometric data and then by follow-up spectroscopy to confirm their nature, but then this takes a lot of telescope time. So alternatively, a more efficient way to do this is to use the unique spectral features that are present, for instance, the prominent water band feature that is present in these cool objects due to the cool atmospheres. So we have used a novel water band based technique to identify the brown dwarfs, which basically combines the data from a custom made medium water band filter, which is centered at 1.45 micron, and this combines the data from the broadband JNH filters, all of them from the 3.6 meter CFHT wirecam instrument. And by this we can photometrically identify the brown dwarfs which have strong water absorption in their atmospheres and distinguish them from the reddened field contaminants. So we've used this color criterion to identify the candidate brown dwarfs, for which we've done follow-up spectroscopy with the 4-meter NASA Infrared Telescope Facility SPECS instrument in low resolution mode. And we had around 30 targets that we observed, and this is the spectra for them. So they are stacked in terms of their spectral type, so it starts from M3 down to M8.5. And we can clearly see that as we move down to the cooler objects, we see a characteristic peaky or like a triangular shaped H-band continuum due to the water absorption on either side. So this is the deepest survey of substellar objects that has been done for this region, probing down to the planetary mass regime. And with the newly identified brown dwarfs combined with the literature members, we have compiled a comprehensive catalog of confirmed members in this region across a wide mass range from 19 solar mass down to 4 Jupiter masses, which corresponds to spectral type of O9.5 to L5. And with this catalog, we have traced the initial mass function for the Sigma Orionis region. And here we have two functional forms that are fit to it. One is a log normal distribution and the other is a segmented power law fit. And we checked the results of both the functional forms with the slope of other young star forming regions in different environments, and we found the results to be consistent. So this in turn shows that the environment does not play a significant role in shaping the initial mass function, both at the stellar and the substellar regime. So this is the deepest IMF that has been reported for this region with a robust sample of confirmed members probing down to almost 4 Jupiter masses. And in the second part of the work, we have characterized the disk around the YSOs in this region, and in doing so, we have explored the formation mechanism of brown dwarfs. So firstly, we have classified the YSOs into various evolutionary stages that I mentioned in the introduction, like class 0 to class 3 objects, by using the slope of the spectral energy distribution between 2 to 22 micron, and these objects are highlighted here in different colors. So with this classification, we then estimated the fractional population of disk bearing objects in the region, and we found the percentage to be around 41%. And we found the correlation of this disk fraction with the cluster age, and this correlation was consistent with the general trend that we see for star forming regions in low UV environments. Now since we have used mid-infrared data, we are probing the inner disk region, and what does this correlation tell us is that the external photoevaporation due to the massive star that is present in the center of the cluster does not have a very predominant effect in clearing out the inner disk of the YSOs in this region. And finally, we found the correlation between disk fraction and stellar mass, and one of the key observations here was that more than 50% of the brown dwarf population was found to have a disk around it. So with this, we see that it's possibly indicating towards the dominant formation mechanism of these objects being similar to a scaled down version of how the low mass stars form through the gravitational collapse of the GMC. So I'll quickly segue into the next region that we have. So we have IC 1848 East and West. Now these two clusters are located in the distant massive star forming complex called the W5 Giant Molecular Cloud Complex. And what is unique about these two objects is that both of them share similar characteristics in terms of age, distance and low extinction. But the West cluster experiences almost 4 times more FUV flux than the East cluster due to the number of massive stars that are present in it. So because of these similar characteristics, we refer to them as the twin clusters. And for this study, we have used a multi-wavelength data set in optical NIR and MIR wavelengths. And one thing that I need to mention here is that the Spitzer data that we have used comes from a dedicated Spitzer imaging survey of the H2 regions in the W5 complex. So because of this, the Spitzer data that we have used is almost 4 times deeper than the Spitzer archival data. So because of that, we are able to probe down to the substellar boundary in this distant star forming regions, which are almost at 2.2 kpc. So yeah, so here we have used the spectral energy distribution to find the physical parameters like effective temperature and luminosity for the cluster members. And we trace their distribution in the HR diagram to filter out the pre-main sequence sources, which are highlighted here in both the color magnitude diagrams. So the CMD on the extreme right is the DOT R-band observation and the data from the new form K-band photometry. And in both the CMDs, we see that the pre-main sequence sources trace a well-defined pre-main sequence branch. So this shows us that both the clusters have low uniform extinction within the cluster area. And here we found the disk fraction for the East cluster to be 27% and for the West cluster to be 17%. So we see that the overall disk fraction for the West cluster is slightly lower than the East cluster because the West cluster experiences more ionizing radiation due to the higher number of massive stars that are present in it. And we trace the disk fraction as a function of the stellar mass, and what we see is towards the lower masses the trend is almost a constant, which can be ascribed to a prolonged lifetime of the disk around the lower mass stars. But as we move to the higher masses, we see a slight decline in the occurrence of disk around these objects. So this can be attributed to a more accelerated evolution of the disk around higher mass objects. And in general, what we observe in literature is for young star forming regions less than 5 million years, the disk fraction is around 40 to 80%. But given that these twin clusters are young at 2 million years, we are observing a very low disk fraction. So in order to understand the reason for this, we found the correlation of the disk fraction in terms of the strength of the ionizing radiation from the massive stars in terms of FUV flux. And what we have here is, in accordance with the recent theoretical studies, in high UV irradiated regions of more than 10 power 3 G0, there are strong disk winds which can cause higher mass loss rates of more than 10 power minus 6 solar mass per year. And recent modeling studies have shown that if the mass loss rates are really high, then the disk fraction can come down to around 20% at even 2 million years. So that is what we observationally see in both these clusters, wherein both of them experience more than 10 power 3 G0 of FUV flux. And this shows that not just in the center of the cluster close to the massive stars, but the entire cluster is under the influence of the ionizing radiation, which is affecting the disk population. So this underscores the significant role that environment plays in clearing the disk or in the evolution of the circumstellar disk. So to conclude, I'll just talk briefly about the ongoing work on IC 1396, which is again a young star forming region at around 900 parsec. So for this study, we have used deep optical data from Subaru Hypersupreme CAM, and you can see from the color magnitude diagram here, wherein the existing literature members are highlighted in yellow, and it shows the mass limit of the existing membership down to only 0.1 solar mass. But with our deep optical survey, we are probing a new population of substellar objects in this region. And the main idea of this work was to conduct a deep spectroscopic survey of these substellar objects in IC 1396. And for that we have taken data from two telescopes. One is from the infrared telescope facility SPECS instrument, and the other is from GTC. GTC is a 10-meter class telescope, and we've used the EMIR instrument, which is a near infrared multi-object spectrograph, and it was installed in late 2017. So we've used these two instruments to observe these substellar objects, and this is a sample spectra of one of the objects that we observed, which is an M8 type object. And with this survey, we have identified a new population of brown dwarfs in a distant star forming region at around 1 kpc. So this is an ongoing work, and we plan to characterize the disk around brown dwarfs and their relation to the stellar environment. So these are the key results of my work. Firstly, we have improved the detection of brown dwarfs by using a novel water band based technique. Secondly, in terms of the substellar initial mass function, we do not find any significant evidence that environment plays a role in shaping the initial mass function. Thirdly, we find that brown dwarfs dominantly form through a similar mechanism that forms low mass stars. And finally, the stellar environment plays a very crucial role in the evolution of the circumstellar disks. So this is some of the future scopes out of the thesis. So I'm currently, for my postdoc, I'm working with JWST data to study the planetary mass objects and to test the conditions for planet formation in their disk around them. And from this thesis, we can also look at high angular resolution observations to look for planetary mass companions to primaries that are below the deuterium burning mass limit. And also we can look at the effect of massive stars on brown dwarf formation, and also spectroscopic study of planetary mass objects which are identified in target regions in this study with bigger class telescopes can be done. So I'll leave you with the summary slide, and thank you for listening.
We also have jury members, I forgot to mention, Manoj. So, any questions from the jury members?
So, while estimating the mass of the disk, you basically ionizing EV flux from massive stars are also involved, right?
Sorry, sir, can you come again?
So, how do you estimate mass of the disk?
We're not estimating the mass of the disk, it was the stellar mass.
20% or 30%, whatever you say.
You mean this one?
Basically, basically massive stars or radiation from massive stars, ionization and particles in the disk, and that is how you estimate the composition of disk.
Mm-hmm.
So, do you know how much of radiation, ionization is coming so that this much of mass is being estimated from the disk?
Okay, so
No,
this one?
Yeah, okay, this one, yes.
So here this is the total ionizing radiation that we get from all the massive stars. So
How do you get that?
So we have the spectral type to the FUV flux standard relations. So for the number of stars that we have, we find the total FUV flux that's irradiated by the center of the cluster. So for instance, one of the clusters has around 6 O-type stars, and the other one has around 4 O-type stars. And each of them have a spectral type and an associated number of photons that are, the FUV photons that are emitting from literature. So we find the total for all the massive stars that are present, and for each source in the region, calculating the distance from the center of the cluster to the distance, we estimate the amount of flux that each target would, each source would receive, and then we bin it in terms of the FUV flux that the entire cluster receives. So that is what you have here. So that's the total FUV flux given by the center of the cluster. So all the massive stars at the center of the cluster.
Okay. So in another question, like you showed the deviation of our distribution IMF at low mass range. Deviation of distribution IMF at low mass range. Initial slides.
Mm-hmm.
Yeah. So observational bias might be
Yes, that is the possibility, because it is very difficult to observe these objects because they are very low luminosity, and even if we do, then the observations are restricted to the nearby star forming regions. So for distant star forming regions, we need higher telescope observations, and secondly, we need a low extinction environment. So all the targets that we have are low extinction environments, so that's one of the reasons that we are able to probe these substellar objects which are at such low luminosity and low mass.
Somewhat continuing the same question. So what you are saying is that you have a very luminous star nearby, which shortens the disk for the planet, for the lunar star to form, right?
Yeah.
Okay. The question is, what are the factors other than if it is not very close to a luminous star, right?
Mm-hmm.
So what are other factors that will determine the size of the disk?
Okay, so in terms of the environmental effect, if you're talking, so the major environmental effect comes from the massive stars, but apart from that, there are also the tidal truncation due to the close encounters from, if it's a really dense environment, then due to close encounters, the tidal truncation can also affect the disk properties, but then that has been shown to have only very low effect on the disk evolution. Only extremely high density environments like more than 10 power 4 stars per parsec square environments can have an effect, but the regions that we generally see are, they do not have such density. So that is not a significant factor. And secondly, also metallicity can play a role, but here the regions that we have considered are all solar metallicity regions, but we need to look at outer galaxy regions if we want to see what is the role of metallicity in the evolution of these disks. Yeah.
May I ask something? Okay, so I mean, you sort of tried to figure out, and one of the conclusion is that the processes that form the brown dwarfs and the low mass stars are similar, right? But yet brown dwarfs are not so low mass stars.
No.
So are there any a number of factors, crucial factors that will determine a formation of brown dwarfs and not low mass stars?
Okay, so brown dwarfs, by definition, there are two ways of defining brown dwarfs. One is based on their mass range. So if they have a mass below the hydrogen burning mass limit, which is 0.08, then we call them as brown dwarfs. The other definition is based on their formation scenario. So if there are again 4 different theories that say how brown dwarfs form. One is similar to the low mass star formation. The other is through the gravitational instability of the circumstellar disk, which says they form like planets. We also have a theory which says that if the prestellar core is close to a high ionizing O-type star, then due to the radiation from this O-type star, before the prestellar core can collapse and start hydrogen fusion, the radiation from the O-type star will kind of eat out the envelope that's around the prestellar core, so the core doesn't get sufficient materials to start hydrogen fusion. So that's another theory. And fourth one is, if it's a multiple system, then the lowest mass object in the multiple system will get ejected out before it can gather enough mass and temperature to start hydrogen fusion. So that is another way of how brown dwarfs can form.
So we have a last one, and maybe after you, if there's some questions on that.
Melinda, I have a question on towards the end. You talked about ongoing work, and you showed a couple of slides. A couple of slides in prep.
This one or?
In preparation.
Yeah, in preparation. Yeah. So next, are these plots in your thesis?
Yes. Yeah, it's there.
So, anybody from the audience, any questions? Okay, let's thank Belinda for a very
Thank
you. So, the next presentation is by Prerna. This was on unraveling the kinematics and dynamics and structure of galaxies using H121 centimeter observations. Thanks, Manoj, for keeping the time. So we have 20 minutes for presentation and 5 minutes for questions. Yeah, I also want to note that the first round of screening, the juries noted that work, and the presentation quality was very good, and it was very hard to shortlist 4 out of the 8 presentations in the earlier round.
Hello. So,
so after 15 minutes, I will ring the bell and show you 5 minutes remaining. And after 18 minutes also, I'll ring a bell and I'll ask you to show the go to the conclusions.
okay.
So we are very tight on.
Next, previous, and mouse pointer. If you move it
Okay.
over, the mouse pointer will move.
Next previous. Am I audible, right? Yeah. Okay. Hello everyone, welcome to my talk. So I will be talking about the kinematics, dynamics and the structures of the galaxies unrevealed through the H1 21 centimeter observation. Yeah. So atomic hydrogen or H1 is one of the most important baryonic component of the galaxies, because from it we can probe those galaxies properties that usually cannot be probed through single disk observation or observation from the other wavelength. For example, the largest radial extent of the H1 in comparison to optical or infrared disk makes it usable to probe various galaxy distances about up to a very large radius. Besides that, from the single disk observation we get those quantities, only the global quantities like the mass, the velocity, velocity widths, etc. But through the H1 interferometric observation we can probe the galaxy's kinematics, dynamics and structures in a resolved manner. So throughout my thesis I have worked on different important studies in this field, and I will be discussing them one by one. So first of all, now we started with archival data. During the last 4 decades there are several H1 archival surveys and observations done, and there exists a large number of the archival data already in the archive, and these observations have been made with different setups, sensitivity, spectral and velocity resolution. It has now become important to check the coverage and the completions of the data set so that we can get an idea of the sources that has already been observed. And besides that, these data which are in the archive for a significant fractions of the observed data, there is no reported results. Also, the data analysis is very heterogeneous, and often, currently through this time, for some key analysis, better, more accurate and advanced method in comparison to the ones that have been used earlier is now available. So considering these points, it will be beneficiary and very useful to do the check the archive and find out that what best data we already have. And in order to do that, we have started out doing this exercise, which is this GMRT archive atomic gas survey, which consists of the good quality archive data from the GMRT, and we have put several criteria to find out this sample set. For example, the data that which has channel width less than 35 kilohertz, so that the data has been observed in spectral line mode. Then on source time greater than 1 hour, which says that the data has high quality, high sensitivity data is there. And then we have made the cutoff of observation frequencies and the velocities to ensure that the data is of emission lines, not from the absorption lines or some absorption lines, and we can observe the H1 in these galaxies in a resolved manner, because beyond this frequency or redshift it is hard to get the data in a resolved H1 data in a resolved manner, at least with the existing interferometers. And then also excluded the galactic sources within plus minus 10 degree of the galactic latitude. So this consists of a sample of around 500 sources, and including 46 ellipticals, and these 500 sources are actually the finalized sources for the Garcia. And we intend to analyze these data uniformly and make the data products publicly available in a phased manner. And in order to do that, okay, you can also check out our website that we made to get the details of this survey. And yeah, so in order to go through this big survey, we first started out with an 11 sample as a prefatory work, made it as a pilot survey, and most of my thesis work is dependent on these 11 galaxies, so that the science cases that we can perform through these 11 galaxies can be applied through the rest of the sources. And these galaxies is a representative sample of the whole sample. As you can see, the red stars over here. The blue stars are the whole sample, and the red stars are the sample from the pilot survey. They are bright, nearby, and has a good range of the masses, and the inclination and positions angles also have a good range, so that we can, there is no biasness in the pilot sample. Okay. Now, once I have talked about the pilot sample, I'll briefly tell about that how the data analysis has been done. The data analysis has been done using some semi-automated routines from the techniques from using the apes, like and standard calibration technique, the flagging, calibration, image, continuum image and subtraction, and 3D image cubes with different resolution, making the making use of the different robust scheme and UV coverages. So once with the analyzed data, here are some data products. This is a schematic diagram of the data cube. We have also obtained the moment maps, and then the H1 spectra and the column density histograms for all these sources. Now, as I have promised in the beginning that with this data product we have been investigating several science cases. So among that, first I should mention that we have checked with the data product this mass size relation with the existing relation in the literature, and we find out that our data products are matching quite well with these existing relations, which gives us the confidence to go ahead and do the rest of the science cases that we intended to do. Now, as a first one, we have looked for the cold and the warm neutral medium of the ISM, and with the Gaussian decomposition method. This method actually takes spectra at each pixels and decompose them into multiple Gaussian, and we then take the full width half maxima of these Gaussians and check its histogram, and find out that in each cases of all these 11 samples there is a signature of bimodality, and the cold gas fraction varies from galaxy to galaxies in a wide range. And the important feature is that the cold gas is around the outskirts of the galaxies and the warm gas in the center of the galaxies. And also our technique, our technique, the novelty of this technique, it works at lower SNR of SNR 5. So in the most of the previous works, this study was limited to SNR 10, and in our case, we have checked that it works reasonably well in lower SNR, and which results in a detection of the more cold gases. Now, I will go to the next science case that we have approached, which is the kinematic modeling of the sources. Now, in the previously, most of the studies, the kinematical modeling have been performed using the 2D technique, that is fitting the tilted ring model, 2D tilted ring model in a 2-dimensional velocity field, but this has some drawbacks. So what we are doing is that we are fitting the 3-dimensional tilted ring model in a 3-dimensional data cube, and the utility of it that this 2-dimensional kinematical modeling is limited for the limited range of inclination, because of it get affected by the beam smearing and the projection effect, but the 3-dimensional kinetic model doesn't get affected by this beam smearing and the projection effect. And previous studies by Campus et al., they have showed that if we find out the kinematics, for example, the velocity or the inclinations, from 2D and 3D method, there are clear, there are clear differences between the 2D and the 3D method. So this tells us to make the kinematics accurate to study the further cases. So to do the 3D kinematical modeling, what we have made use of the most two popularly available pipelines, which is the FAT and the B-Barlow. And we have run these two pipelines and checked the PV diagram, the residual maps to finalize that for which kinematical model we should use, and then finalized our rotation curve. And I should mention that we checked that for most of the cases FAT gives better results than the B-Barlow. Okay, now equipped with the kinematical, 3D accurate kinematical models, we then check the mass modeling of these galaxies. And as you know, there always has been, this debate about the discrepancy between the, observed rotation curves and the rotation curves that can be, yes. So for the mass modeling, there are several other studies done previously for doing the mass, where the mass modeling have been studied. But in those cases, there are some limitations. For example, the scatter in the mass to light ratios makes it very difficult to constrain the stellar velocity component and also the accurate estimations of the rotation curve. Most of the previous studies of the mass model have used the 2D rotation curve for doing the mass modeling, but now we can say that the 3D rotation curves are more accurate to do the mass modeling, and also most of the previous studies have not included the gas component. Now, if we so for the stellar component, what we have done is take the data from the Spitzer and the SDSS telescopes, and we have solved this Jeans anisotropic equation, and by taking the surface density brightness from the multi-Gaussian expansion techniques. Now, the use of this multi-Gaussian expansion technique is that if you, finding the surface brightness is that if you have a in previously what people used to do is to take the ellipses fitted to the brightest or the largest contours of the galaxies, but in our cases we are using it because if you fit an ellipse which is to a contour which divides very deviates from the ellipse, for example, if you have a spiral arm or if you have bar-like structures, then this ellipse fitting method doesn't work well. But as the Gaussian is a complete set of functions, then the surface brightness can be explained better if we use this technique. And here for finding the star velocity component, we have the mass to light ratio in our as a free parameter in our model. And for the gas velocity component, we are considering the galactic disk to be rather thin potential, and we got the kinematic surface brightness of the gas from the 3D kinematically model, and we have performed this integration numerically in most of the previous studies. This integration haven't been done numerically, and they have made an empirical assumption on this sigma and then perform this integration, but we have made our way to do these integrations numerically. And well, for the dark matter halo, we are using the NFW profile. Now, why we are using only the NFW profile? Because previously people have seen that if we have been using the 3D kinematical modeled rotation curve while doing the mass modeling, this NFW works better, at least for the dwarf galaxies. So equipped with that, the free parameters in our model becomes this mass to light ratio, M200, the halo mass, and the concentration parameter. Now we make use of we approach this problem in a Bayesian way, and use the Markov chain Monte Carlo optimization method for performing the fitting. And we should mention that I mean the priors that we have selected for doing this mass modeling are totally based on the observations, not on the existing scaling relations. I mean, in most of the previous studies, or mainly all of the previous studies, these priors have been selected on the scaling relations, existing scaling relations, which assumes that well, these relations already exist, but we are not doing it here. We are doing it in purely, getting the priors from purely observational constraints. Now, yeah, so here's are the results of the mass modeling. As you can see that our results matches quite well with the observation data, which tells us that the process of the mass modeling that we have been following is robust and gives quite good results. And to check the consistency of the parameters that we have been found, we checked the data. We checked our results, that is found the M star, the M gas and M200 with the previous observation, and also the scaling relations which comes from the n-body simulations. And as you can see that these results are pretty consistent, which tells us that the process of our mass modeling is robust and can be applied for the all next batches of the Garcia sources. Okay. Now, to summarize the mass model, I should mention, sorry. I should mention that, yes, 5 minutes, yeah. I should mention that I mean 3D extended rotation curve plus JAM plus MG modeling and the MCMC optimization process and the derivation of the gas, these all together, I mean, haven't been put all together before for doing the mass modeling, and we have done it, put it together and find our way out to do the robust mass modeling. Now, after that, the next project I will talk about the lopsidedness of the galaxies, and this in the lopsidedness, what we have studied, there is asymmetric in the observed brightness temperatures of the galaxies, and which we can find out from the Fourier analysis and it is observed both in the stellars and the gastics. Now, it has been reported in the literature that this lopsidedness may not be solely due to the interactions from the pair or the environment, and it can be a generic trend of these galaxies. And if we consider that, then it can also be result from a lopsided halo, and there is this lopsided halo perturbation parameter epsilon, and that can be found out both from the morphological lopsidedness and the lopsidedness coming from the kinematics of the galaxies. Now, previous results, as these two, epsilon 1 and epsilon kinematics are coming from the same potential, so this should be similar. But in the previous studies, people have found that these parameters are not similar, depends on the differences in the rotation curve. But in our case, what we found that if we use the 3D kinematical modeled rotation curve in our cases, then these two parameters are similar, and we can get, though our sample set is small, but with the recent or the upcoming data from the Garcia, it can be stated with better statistical significance. These are consistent. Then I go to my next project, which is the baryonic-Tully-Fisher relation. So as we will all know that this is one of the most fundamental relation in astrophysics. Now, to establish that relation, most of the previous studies use this there are different forms of the velocities, and some of them comes from the single disk observations, and these single disk, widths of the single disk observation in most of the previous studies have been corrected for the optical or inclinations from the 2D model. And there are some cases where the the velocities have been used from the rotation curve, which comes from the kinematical modeling, but these are also mainly from the 2D kinematical models. Now, there are differences in the inclination if we measure from the moment zero or the optical map from the kinematics, and also in terms of the velocities, which tells us that these relations need to be revisited. And we are revisiting these relations with a set of some galaxies, Garcia, 11 galaxies from Garcia and also some galaxies from the Califa. And these Califa galaxies we observed later part of my, after the Garcia paper came out, and analyzed the data of the Califa, and there H1 was detected for 11 sources. Then similar with the kinematics and the mass modeling of the Garcia sources, perform the kinematic modeling and the mass modeling of the Califa sources, and the successful mass model could be obtained for 7 sources. The reason behind it is that many of them were in quenching stages, and the finalized sources for baryonic to fission relation is 18. And
please go to the conclusion.
Yes. So in conclusion, I will say that the baryonic to fission relation that we are getting has a shallower slope and in comparison to the existing one, but as the sample is only with 18, we need more samples to state that with statistical significance. But the point is that this relation has already been published with the 11 sources in Bishas et al. 2023. But later in my thesis, I have included these other sources from the Califa, and the results were unchanged. Okay, so with that, I will conclude. Here is my conclusion. Thank you.
Yeah, thanks, Prerna. So we have time for questions.
Conclusions.
Anyone from the audience? Okay, so we'll go to the jury members.
Yes.
Brenda, I need a clarification. What is the difference between 3D modeling, kinematic modeling, and 2D kinematic modeling? What extra did you do?
In the 2D kinematical model, you fit a two-dimensional tilted mean model. I mean, two-dimensional means you will have modeling the galaxies ring by ring, and in each ring you have a fixed inclination, the position angle may vary, but the ring is at a plane, 2D plane, and we are doing it with the two-dimensional velocity field. But if you have two-dimensional velocity field, then it get affected by the beam smearing and the projection effect, which is coming lot of line of sight in a singular beam. But if we use the 3D kinematical model, which is the modeling the galaxy in a tilted rings, each rings can have its individual inclination, positions, angle, velocity, and also the dispersion velocity, etc. And use the data cube instead of the 2D velocity field, then this is not affected by the beam smearing and the projection effect. So it's the more accurate and the better one.
Yeah.
How do you estimate the inclinations while they are switching from 2D to 3D?
Inclination is a free parameter while we are fitting these models. It varies from ring to ring. So we have the data product or the data cube, and we are fitting it to that ring, which varies. Different. The ring size is actually the equals to the beam size that in the data, and it checks that at which inclinations the data fits on that particular ring. So ultimately, what we get is a inclination as a function of the radius, and we take the median of that inclination as the kinematic inclinations of these sources.
Okay, so actually I might have missed. Basically, some of the results you are basically either agreeing to the existing models or something like that?
Not particularly. In fact, we are telling that the studies where the 3D kinematical modeled, 2D kinematics or modeled were used previously, these studies need to be verified with the 3D kinematically modeled results. That from one that comes the mass modeling, second comes the consistency of the halo perturbation parameter, and also the baryonic to Fisher relations. So all of these also need some other advancement from other things, but the 3D to 2D, that is one of the most important things that need to be encountered while revisiting these studies.
A lot of good work, but I just want to ask you, so what is the most important new and unique result that have come out of your thesis? And if I were to ask, what would be your response?
Okay.
Just one.
Okay,
The
so
new and unique.
Okay, the new and unique that that just I mentioned, that the results that or the data that are already in archive and the analysis that have been followed previously are now evolved in a better analysis procedures, for example this 2D to 3D, and we need to study these relations with the new techniques to check if.
So it's not the result, but it's a new method or something that you have developed.
Yes, our results. Yes, our results suggest that these studies need to be rechecked and re-verified because they are differentiating even with this smaller sample.
What is the title? Understand or kinematics of the thing.
Yes.
So what kinematics have you understood from you?
Okay, so the kinematics that we understand that I mean we have find out that sorry, it just goes back. Yeah, I will just tell. I mean finding out the rotation curves of the individual galaxies is itself like understanding these galaxies separately. And secondly, the mass modeling that we have built are very robust and haven't been this technique haven't been followed earlier to anywhere. And the mass modeling that we are giving to the scientific community as a fair guiding principle, that actually tells how the masses and the structures are distributed over the galaxy. So even if we forget about the upcoming one to check the scale relationships and all those, for these 11 galaxies only, these studies shows us the structures and the dynamics of galaxies overall. And also we study these asymmetric natures of the galaxies and how the halo perturbation parameters varies and can be similar found from the both the ways. So yeah, I mean apart from the scaling relation, these are the understanding of the kinematics, dynamics and structures that we found out.
Yeah, thank you, Prerna. Do you have any final questions from the audience? Yeah, I don't see. So let's thank Prerna for that. So our next presentation is by Vikas Soni on the effect of metallicities and the effect of metallicity and So Vikas, 20 minutes for the presentation, Vikas.
So, thank you for the organizing committee for giving me an opportunity to present my thesis work in this big range of audience. So, myself Vikas Soni, and I did my PhD under the guidance of Kingshuk Acharya, and the title of my thesis was the effect of metallicity and the vertical mixing on the abundance of major HNCO bearing species in the atmosphere of exoplanets. So there are few talks already have been talked about what are the diversity of this planet that they gives us. So some of the statistical studies suggest that each star has at least one planet around it. So if you want to say our star in our Milky Way, it's come out to 10 to the power 11. So till now we have more than 5,800 exoplanets got discovered. So as more and more these exoplanets have been discovered, so they come out to be very diverse in the parameter space as well as very different from a solar system planet. And some of these planets are also challenge our understanding in the theoretical understanding of this how the planet form. So if you see this plot, so this plot shows the planet mass versus separation. So each dot corresponding to one of the observed exoplanet. So you see the range of this mass is around like 5 order of magnitude. In the radius part, you have 2 order of magnitude radius diversity. So you also see the temperature of the planet. The temperature of the planet goes as much as like more than 2500 Kelvin. So these make a very diverse set of planetary zoo. So the other parameter is the metallicity that has not much talk about in this conference. So the metallicity, atmospheric metallicity means the abundance of the metal with respect to the hydrogen, like how much heavy metal abundant in your atmosphere comparatively hydrogen. Here I means metal means all the element other than hydrogen, helium. So these elements are necessary to form the molecule in the first place. So if you see this plot, this is the first plot. So this plot shows how your oxygen and carbon is varying within your disk. So where the planet form and how the planet is migrating within your disk, that is give you the what will be the final metallicity of your planet. So constraining the metallicity of your planet, you can also talk about or can get a hint how this planet was formed. So this, okay, sorry. So this, the second plot is showing the observed metallicity range of the planet, of some of the planet. So this also show a very diverse set of range. It's come out to like a 5 order of magnitude, like very low as 0.01 solar metallicity to like more than 1000 times solar metallicity. So the metallicity range that I have taken for this study is like 0.1 to 1000 times solar. Solar metallicity means 1 solar means whatever the metal abundance in your atmosphere is, it is as compared to solar one. So 10 times means you have a 10 times more solar, 10 times more metal in your atmosphere comparatively solar abundance. So how do you observe this atmosphere in the first place to get a hint about the metallicity? So one of the major method is the transit method. So in which you observe the brightness of a star, and when your system is edge on, so you see a dip in the brightness of your star as a planet is passing by. So now if you put the atmosphere on a planet, so this dip is slightly larger due to atmosphere offer you some extra extension to your light. So in that this dip we also, sorry. So this dip we call as a transit dip. So now in your atmosphere you have several molecules are present, as well as this molecule have a different abundance also. So each of the molecule have the wavelength dependent cross section, which means if you see the atmosphere in different wavelength, so the different molecule will absorb different amount of light. So if you change your wavelength, so that now the color coding is the changing your wavelength, so your atmosphere will look like either the radius will change, or that you can measure by the transit depth. So if you measure transit depth with wavelength, so you call this as the transit curve. So in this transit curve you will find the signature of the molecule that are present in your atmosphere, as well as also you can also constrain the abundance of your molecule in the atmosphere. So now till now there are several molecules have been detected, like what is the most common one, but my thesis only focus of some of the molecules that are very important in the term of habitability. So these molecules are basically like hydrogen, carbon, oxygen, nitrogen bearing molecule. So in this plot I have, so in this figure I have plotted which of the planet, which are the molecule that I have detected, that on which I am interested on. So like, and each of the color circles represent one of the molecule. So now the main goal of the thesis is to understand how the metallicity will affect the abundance of this atmospheric abundance of this molecule in your atmosphere, as well as we also have a aim to find the parameter space on which are the following molecule can be easily observed. And also in the last part we also try to incorporate the disequilibrium process in the atmospheric retrieval. So this is basically the first step in distinguish the true biosignature from the false one. So now I come to the equilibrium chemistry result. So in the equilibrium chemistry means in your system you have several molecules, and these molecules are continuously reacting with each other. So some molecules are formed during a reaction, some molecules are lost. So in a steady state, what happens, your production rate of a specific molecule do all of the reaction will be equal to the production, it will be equal to the loss rate of your molecule due to all the reaction. So this state we call a steady state. So if your system does not involve any dynamic processes, so we call that abundance as a equilibrium abundance. So here I will show the like divide and understand rule. So in which we divide our parameter space like pressure, temperature, space in two parts. So this line, divide your parameter space in the hydrogen, in the CO dominant region and the CH4 dominant region. So which means the right side of this part, like it's a planet lies right side of this part, the planet atmosphere will be dominated by the CO. In the left side it will dominate by the CH4. Now if you change your metallicity means you put more and more carbon oxygen in your atmosphere, so how your abundance will change. So if you increase your metallicity, so this curve shifted toward the left side of your plot, means the lower temperature, means the planet which previously have the CH4 is a major constituent of carbon in our atmosphere, now it replaced by CO. The same goes for N2 and NS3. But if you, so this orange to black color curve represent the CO2 versus CO boundary, which says that if you increase your metallicity in the atmosphere, your CO2 abundance start to increase and overcome the CO abundance at some point. Now this is, now we can also quantify this abundance. So this plot show for a specific pressure range. This is for the 1 millibar pressure. So now we again divide your parameter by this black line. This black line dividing, sorry. So this black line is dividing in the CO region and the CH4 region. So it is interesting to see that if you, so in the x-axis you are increasing your metallicity, means even if you increase your metallicity, your CH4 abundance does not increase in the CO dominant region. As well as if you go for the HCN also, in the CO dominant region, HCN does not show any significant effect of metallicity in its abundance. But in your atmosphere, chemical reaction are the one part, the other processes are also involving simultaneously. So you also have the transport in which your molecule are from the lower layer can transport to the upper layer, as well as from the upper layer of molecule can be transported back to the lower layer. So this break your thermochemical equilibrium abundance, because the molecule that should not be present here, that will both from the lower part of your atmosphere. In the upper part, you also have the photochemistry in which your stellar radiation will break some of the molecule and makes free radical. This free radical further reacts with the other molecules that are present in your atmosphere. So what we will do, so what we have done, so we develop a 1D disequilibrium model. So this divide your atmosphere in n layer. So for each of the layer is solve this mass continuity equation, and this PIN are the production term and loss term, and this the third term is the transport term. So this is the India's in-house fully developed disequilibrium code specialized in the exoplanet atmosphere. But now you want to understand where these processes are dominant in your atmosphere. So in the deep of your atmosphere, your temperature is high as well as your density is very high. So in this regard, your chemical reaction are very fast. So the chemical reaction overcome all the dynamic process happening in the deep in the atmosphere. But as you move up in the atmosphere, your chemical reaction becomes lower and the vertical mixing start to dominate. In the upper part, the photochemistry is dominate. So now if you see which part of your atmosphere will generate or have the large contribution in your spectral signature. So the lower part is very optically thick and the upper part is very optically thin. So in the upper part you have the contribution of the spectral signature in the upper part is very low. So but in the middle part, most of the spectral signatures are get generated. So this middle part is dominated by the vertical mixing. So now you can also divide your this mass continuity equation in two parts. In the one part is the chemical part and the other part is transport part. So you can define or you can give a time scale on both the part. So if you see this plot, this is the CH4 mole from the CH4 abundance, how it's changing with the pressure. So this different color represent different strength of the mixing. So you see, if you change your mixing strength, your different color means this color bar are the output of the 1D photochemical transport model. So at some point of time, this CH4 abundance follow its equilibrium counterpart. As soon as it hit a point, so it become quench at the particular value. So what this point represents, this point is where your chemical time scale R is compared to the vertical mixing time scale. So if you can get the information of the quench level, like this level, as well as what will be the equilibrium abundance at that point, you can get what will be your abundance in the presence of transport. So to find the chemical time scale, we did a detailed chemical network analysis in which we find like there are several pathways by which CH4 and CO get interconvert, but the chemical time scale are only dependent which is the fastest pathway among them. So this color code are giving in which of the parameter space which are the reaction are dominating. So this in the pressure, temperature as well as the metallicity. So changing the metallicity, some of the reaction, the dominant reaction path will also change. So this is for the nitrogen species. So to have the time scale of the vertical mixing, we use the mixing length theory in which what we did, so the mixing length theory is given by the your mixing length square divided by ED diffusion coefficient. So now we can again, having the information of chemical time scale and the vertical mixing time scale, we again can divide your atmosphere in two part, or the parameter space in two part. So in one part your chemical time scale is very fast, in the other part your vertical mixing time scale is dominating. So the planet which fall in this part will dominate by, or you can approximate their abundance by thermochemical equilibrium abundance, and in this part you have to require to enforce the vertical mixing. So this is for CH4 and this is for CO. Now if you change your metallicity, so this is for -1 metallicity means 0.1 solar metallicity. If you change your metallicity, your molecular abundance will change. So as a result, your this Quinch curve will also change. So these are the curve that we are proposing to the committee the first time. So we call it the Quinch curve. So if you, these are the intermediate metallicity. Now if you change your transport strength, means how strong your mixing is, so according to which your Quinch point will move up and down. So if you like Kg for solid, if you for the solid one, the Quinch level are far in the lower temperature compared to the vertical mixing which have higher strength like Kgz or 12, the dotted dash line. So we can use this quenching approximation to do a lots of cool things. So one of the result is to understand or to constrain the metallicity of the VASP 39b. So what we did, we run our model and compare the output of the model with the observed abundance of CO, CO2 and H2O. So you can see here, so this dotted line, so this dotted line are the our output, and the dash and the solid one are the observed abundance. So you see this only for one solar metallicity it matches well, but for the lower metallicity like -1 and 0, it either overshoot your abundance or is undershoot your abundance. So in one of the work we also try to find like what are the like in which of the planet you can have the HCN and the NS3. So for it what we did, so we make a grid in the equilibrium temperature and the internal temperature. So these are the, equilibrium temperature range from 800 to 1700 and the internal temperature range from 150 Kelvin to 400 Kelvin. We also take the different gravity, like this for G is equal to 5 and this is for 15 and this the lower one is for 45, as well as different Kgz value. Kgz value means different mixing strength. So in the x-axis if you move, you are increasing your equilibrium temperature, means you are getting far away from your star, and in the in the y-axis if you move upward, your internal temperature is increasing, means you are getting to the younger and younger system. So this color represent, or the lighter the color, the more abundance your planet have. So if you see in the lower part, so if you move to the equilibrium, to higher equilibrium temperature, means closer to the star. So at a particular value your HCN abundance get peak and then start to decrease. As well as if you change your internal temperature, so the lower internal temperature you have higher abundance of HCN. But in the case of NS3, so NS3 does not change much initially with your equilibrium temperature, but as soon as it hit a particular critical value, after that it drop very sharply. So which means the older planet with intermediate distance from a star, the older planet with intermediate distance from the star, you have a HCN, you can find the HCN, and the NS3 you have to look for the planet which is the older planet with the larger distance from the star. So these are the few planets that we propose, or that are the potential target to discover finding the HCN. So the top 3 are in our list has already found, and these are the top other 3 that we are proposing. So now this so now other thing is this we can get the abundance, but this abundance also relate to some of the parameter of your planet. So you have a model, so this model has certain free parameter, and this with this free parameter of your atmosphere, you make or you find the atmospheric composition, and then you find the what will your transit spectra will look like. So what you do, let's say you have observation and you try to tune your parameters such a way that your observed spectra will be matched with your model. So this is we call as a retrieval model. So previously this because this retrieval model, this is only 5 parameter that I am showing, but in general the retrieval model can have like 10 to 15 parameter. So it try to find your parameter it try to find your best fit parameter or find the posterior probability distribution in the n dimensional parameter space. So it try to run the 10 to the power 6 to 10 to the power 7 forward model to get the probability distribution of a parameter for one set of data. So this take a very huge computation time. So if you do this with your normal convention 1D model, so that will take like huge time. It is not reasonably computationally reasonable. But what we have, we propose another method which is quenching approximation, which is like 10 to the power 4 order of magnitude faster than the conventional method. So what we did, we make a fast forward model and implement in one of the posterior distribution retrieval method, and we generate the synthetic spectrum of a planet which include the vertical mixing, and we try to fit the data with the model which has only the chemical equilibrium and with the method which have the vertical mixing. So what we find that the planet, so the method that we include the vertical mixing in the model, that is fit very well. So which means the method that we are proposing is can be used to retrieve the parameter for the planet that is dominated by the vertical mixing. So the summary of the talk, like we in this thesis we developed the 3 model. So these 2 models are one of its kind in the India, and these are the one of its kind in community. So in this the 3rd model, so we in the first time we include the nitrogen bearing species in your we use the quenching approximation for the nitrogen bearing species, which was previously thought was not possible. And these are some of the highlight of the thesis. And at the end, so these are the article in which all these 3 models are published. And then thank you.
Thank you, Vikas, sorry. So, for finishing it in time, let's have some questions from the audience. So, let's start the juries.
Okay, yes. So, basically, for your model, you need to have transit spectrum.
Yes, basically this model also works for transit spectrum as the emission spectrum.
So, suppose transit spectrum,
yes.
How many organization bands you need to have? And each observation should be simultaneous, right?
No, I didn't get, sorry.
No, how do you get transit spectrum? Different organs, you need to see the transit.
Yes, yes.
Different organs in bands.
Yes, in bands.
But then you need to have simultaneous observations.
Yes, yes,
bands.
yes.
So, till date, any such observations happening?
Yes, lots of observations happening. Like JWST will give so many observations for that, for this planet. Because this planet transiting around like few hours. For the few hours, they have lots of integration time to get the transit depth.
Okay. So then, what are the input parameters you are taking from transit spectrum and using the model to get the parameters?
Yeah. So this transit spectrum will give. We can give the what kind of molecule and what can be the abundance of this of the molecule in the planet. So this abundance will relate to some of the parameter of a planet. So this model will retrieve this parameter based on that abundance that we are that we are seeing in the transit method. In that way.
What parameters you need to take from the transit spectrum? So what are the input parameters to the model?
Okay. The input parameter of the model are, because there are several parameters, like some of the parameters are the vertical mixing KZZ profile and the metallicity, as well as thermal profile parameter, the radius of the planet, in which term to what is the base layer of your pressure height, as well as some of the stellar parameters are also there.
All these parameters you are getting from somewhere?
No, these are free parameters. Some of them are free parameter. Model free parameter.
Okay, Vikas, nice job. Firstly, you in your or I don't know, as movies, animations, you showed that there are ranges where the composition equilibrium breaks down, right?
Yes, 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 yes.
Right. So in those cases, are you considering thermodynamic equilibrium or of the atmosphere, or the thermodynamic equilibrium of the atmosphere breaks down? I mean, non-equilibrium thermodynamics. What kind of, you understand my question, right? the thermodynamics we use, for example, describe the physics
Yes, yes.
in this room, will be in NTP and it will be
Yes,
a
yes.
equilibrium thermodynamics. That means every step is in quasi-equilibrium.
Yes,
right?
yes, yes.
Okay. But when your composition equilibrium is breaking down, are you still using a equilibrium thermodynamics or it's a non-equilibrium thermodynamics?
No, it is non-equilibrium thermodynamics. These are the model which include the chemical reaction as well as vertical mixing simultaneously. So according to
You are
which,
taking the chemical potential as well.
yes, both the chemical reaction will be the what the probability of the colliding or forming the new molecule. So as soon as
Are
your
you taking the chemical potential?
yes, yes, yes.
Okay.
But atmosphere is so dense. I mean, are you telling that you've done non-LT calculations for the level populations?
No, for the level population we use the LT calculation also. So because the rate that we are using, that is calculated with the local thermochemical equilibrium rates. But yes, but as your molecule move, its surrounding will change, so the temperature will change. So in that your molecule can no longer in your surrounding thermochemical equilibrium. So the rate will update it according to your temperature pressure.
So how good an approximation is that? Because, for example, in Mars, the massive wind goes on. Okay, and one can pretty be sure that the LT locally might break down.
Yes, definitely. Because that's why we have different region where the LT will break, where your local thermal equilibrium will remain, and where your local thermochemical equilibrium composition will not remain. So this in the Mars you have the wind that because this wind will take some of the molecules that should not be part of a local thermochemical equilibrium. So that is why your LT will break. So here also we have the vertical mixing that take the molecule which does not belong to one part and put in the other part. So the composition that we are getting is the final outcome of the model that include the LT, non-LT part also by the mixing as well as the photochemistry.
That is taken care in your code.
Yes, that is taken care in the code.
Okay. Because I have a couple of questions. First, about your chemical disequilibrium model. You say this is the first of its kind in India?
Yes, this not till.
There's a comment here.
For the dedicated to exoplanetary atmosphere.
There's a comment here.
Dedicated to exoplanetary.
This equation is regularly used by people who are wanting
Planetary
to
sciences.
neutrinos and
Yes,
so
yes.
on. Yeah.
Yes, yes. Dedicated to exoplanetary atmosphere only.
Right. But there are similar models have been used by the international community.
Yes, yes,
right?
that is
so
so.
that context was missing from your talk. I mean, where does it? Is it what is unique about your model? Is it that you focus on HCN and NS3, or is it some aspect of the modeling which is unique? Not just in India. I mean, is there anything new about?
Basically, we are focusing on the HCN part here, like how this HCN is, how the chemical time scale of the HCN is affected, or how its time scale will deviate your thermo equilibrium abundance that we are proposing the first time.
Is that new?
Yes, it is new. Yes, other does not. Other previous study has told that this HCN is depend upon the NS3 and the CO, and the NS3 and CO are already quenched well below your atmosphere. Means they are already in your non-local thermochemical equilibrium. So, but we come out that part, and what we find that if we use their non-thermochemical equilibrium counterpart of NS3 and CO, we can still use this for to constrain the HCN abundance.
What is different in your model? Why are you getting this results different from the earlier ones? So, what is new in your model that is giving you this result?
No, previous study does not try to or does not think that can be done or not, but we think and we deep down in the theory and we find this can be done for the molecule that for the molecule like HCN and S3 also, basically HCN.
Can you briefly tell about other model?
Other model, so the other model, what the other model will take, they take a single quench value for all of the species. Like the CO, CH4, they take single, but in reality, each of the molecule have different time scale. So you have to take different quench value for all of the part.
So
that we are implementing in the model.
Yeah,
Yes.
So other question is about HCN and NS3 that you are focusing on.
Yes.
Why these two molecular species? Why would you go after this? Is there any particular motivation why you are they easily observable, or Why or the critical why?
Yes, because the nitrogen are like, if you see the nitrogen bearing species that are very fairly common in your in the context of solar system, right? But if you go for exoplanet, there are only few observations that have confirmed the presence of nitrogen. So the HCN and NH3 are the major dominant species of the nitrogen. If you want to find the nitrogen bearing species, these are the two, because you don't have the signature for N2.
Yeah, but others also have done this. Look for this is quite.
No, it is important in context of habitability also. Habitability, like these are some of the.
Why HCN and NHC are not really considered as
no,
biomarkers?
But these are not the biomarker, but these are the essential to evolve the life in the first place.
Vikas, nice talk. Maybe a very naive question. Have you considered the rotation of the exoplanet in your modeling?
Rotation of the exoplanet?
Yeah.
No, these are the 1D models, so we did not incorporate rotation.
Oh. So do you think that if you consider the rotation?
Yes, definitely. The 3D modeling will be give you a better result compared to 1D modeling, but that have a different part of the. But they have different problems. So the 3D GCM require lots of computation time. So you can't do the retrieval on that 3D GCM. So you have to come with a faster model. So these 1D model are in between.
Thank
you. So I have a question. Like, how would it change all these rate defining reactions when you change the C/O ratio?
Because this each of the reaction rate depends upon temperature, pressure only.
No,
right? No, just a second. No, okay, so we have a network. In the network, each of the reaction rate is defined by temperature and pressure. So of course, we have like 5,000 reactions. So in the 5,000, what we do, we try to trace what are the shortest pathway between 1 and 2. And for each of the parameter space, we try to find out. And if you change the parameter space, your molecular abundance will change. So as soon as molecular abundance will change, your reaction rate will change. So depending upon the reaction rate, we will have a different rate limiting step in a different parameter space. So we make a first of list of all the reaction and then sort it and then find the fastest one. And for the fastest one, what will be the slowest one? That will be your that will define your chemical time scale.
Thank you. So I just have a last question. Like, how would it apply for a tracer like sodium, which is forms and range of layers, like in high resolution exoplanet transistor?
Yes. No, what is the question? Sorry.
The question is atomic species like sodium would form in a range of depths, right? Starting from interior to the photochemical reactions that achieve large scale heights. So how would
no, this model is basically for the HCNO bearing species. The sodium line, people have found so many sodium line like from the hot gas giant planet. But this is directly for how the molecules are forming in the atmosphere of this exoplanet.
Yeah, so it wouldn't, like for example, if you have to model retrieval, if you have to use, you would really get.
Yes, in the retrieval, what we will do is we will use the sodium abundance and the free parameter and then try to find what is the abundance of sodium, the sodium line. But that people use as a free parameter or either by the thermochemical equilibrium abundance. So I am not sure how this sodium will affect by the vertical mixing in your atmosphere. But that can be added in the chemical network. So the chemical network is the only input of this model.
Yeah, thank you. So let's thank Vikas for the interesting and comprehensive talk. And we move on to the next presentation by Manoj Verma. So he would be talking about the suit payload, the detector characterization and the onboard processing for flare studies.
And then after 18 minutes, 2 minutes remaining. So after 18, 19 minutes, you have to show the final. Can you give him this?
Does it reach? No, it doesn't.
Oh, otherwise you can put it up. Goes to the next slide.
It's already downloaded. PDF. Use the PDF.
Next slide, previous slide, and this is a mouse pointer. So if you move it around, your mouse pointer will move around.
Okay, cool. Both the mics are on. Okay. Good afternoon, everyone. My thesis primarily concentrates on the detector characterization, the readout electronics testing, and developing, implementing, and testing the onboard processing algorithm for the solar ultraviolet imaging telescope. Given the time constraint we have, I would like to quickly discuss the results of the detector characterization and then explain the onboard processing part. As you are aware, the Solar Ultraviolet Imaging Telescope SUIT is one of the imaging payloads on board Aditya L1 mission. SUIT observes the sun and takes the full disk image of sun in the near ultraviolet wavelength of 200 to 400 nanometers using 11 spectral bands. And apart from this, SUIT also has a capability to perform onboard processing. We will see what it is now. So one of the major science goals of SUIT is to observe the flares at a very high cadence and from the initial phase of the flare. And in order to do that, we have designed, developed and implemented an onboard processing algorithm, and with this algorithm we are able to achieve high cadence observations, also keeping within the data limit that's the constraint that we have. Now, so this is the SUIT detector that is used. This is one of the very important subsystems of SUIT because this is the one that images the sun. It is a Teledyne CCD which has 4000 pixels by 4000 pixels with a pixel size of 12 micron and a plate scale of 0.7 arc-second pixel, which gives a resolution of 1.4 arc-second per pixel. And since it's a fairly large CCD, it has 4 simultaneous readout channels wherein we can read the entire image using 4 channels simultaneously. And we also, along with a full frame image, there is an option where we can select a region of interest on the CCD and we can read only that part. So these are the detector characterization results. We have measured different detector parameters like the read noise, which is the amount of noise that is produced just because the process of reading the CCD. The gain, which tells you the conversion from the electrons that are produced in the pixel well to the final ADU count on the image. The bias, which is the minimum level that we have. The dark signal, this is the amount, the electrons that are produced without any exposure to the light. The non-linearity, which is the behavior of how the response of the CCD to different electrons or the wavelengths. The charge transfer efficiency is how efficiently the charge is getting transferred over the pixels to the readout amplifier. And the crosstalk is the electronics crosstalk, which can happen in a multi-channel readout wherein different channels are used and are traveling at the same time. And we are able to test all of these and make sure we are getting the values within the accepted range. Now let's move on to the processing electronics. So the processing electronics constitutes these 4 important blocks or modules. The first one is the Helios flare trigger module, wherein Helios is the hard X-ray payload. So we get the signal, the data from the Helios, and we use this data in order to see if there is any flare that is going to happen. The flare localization module, as the name suggests, is wherein we use the suit data in order to find the position of a flare and localize it. The ROA tracking module is where during the flare observations or any other region of interest observations, we don't want our region of interest to leave our specific window, and hence we want to track the region of interest throughout the time of observation, and hence we use this module. And finally, the auto exposure control module is used to automatically control the exposure settings so that during the flare activity, because the intensity will increase, we don't want the CC to saturate, and hence we want to change the exposure automatically depending on the flare intensity. So I want to specifically make it a point that all of these are done on board itself. So there is no human intervention as such, like we just fix the thresholds and limits, and all of this happens on board like when the data is coming. So this is how these modules are interlinked. We have the soft X-ray payload from where we directly get the trigger whenever there is a flare, while we have the hard X-ray payload where we get the data in two simultaneous channels. They are redundant channels. And here is our first module which takes the data from it and use the data to produce a flare. And whenever there is a flare flag coming from this module or directly from the SOLEX, the flare detection and localization module immediately triggers and starts looking for the position of the flare. And whenever it finds the position of the flare, it defines the region of interest and starts the flare observations. And during the flare observations, the flare region is continuously tracked using the tracking module, and also the exposure will be continuously controlled depending on the intensity of the flare. So I will quickly try to explain how these modules work. The Helios flare trigger module receives the data from two simultaneous channels. Since these are redundant channels, we want to assign a specific weight to both of the channels, so that in the future if you think that one of the channel is more noisy than the other, we can adjust the weight or completely cut off a channel. So in the first step, we assign a particular weights M1 and M2, particular weights W1 and W2 to these values, and then we get the final median value. And we use this value to see whether how this value is increasing, so that we will say whether it's a flare signal or not. So there are two conditions it has to meet. The first condition is that the M value, which is the combined value coming from both the signals, has to continuously increase for a given amount of time. That is called the count threshold, which determines for how much time is this increasing. The second thing is, now if we have seen that if it has increased continuously for this amount of time, then we check whether it has met the threshold or not. So this makes sure that whatever signal is coming in this total time, it has the overall increase is more than a given threshold. Once both the conditions are met, that is when we generate a flare trigger. Once a flare trigger is generated, now we go into the flare localization module. In this, we take 2K by 2K binned images. We are taking binned images because the amount of time that is taken to read out an image depends upon whether you are reading the entire image, the 4K by 4K, or if you are binning. If you are reading the entire 4K by 4K image, it takes around 17 to 18 seconds. Hence, we want to perform a 2 by 2 binning so that we can reduce the amount of time by a factor of 4. And once we do this, we use the first image as the reference, and the remaining 3 images we subtract from the first image and get 3 difference images, D1, D2 and D3. And now since each pixels are like very small, we want to like make a region around each pixel, we do a super pixeling or binning them by a factor of 16 or 32, so that we get a super pixels. And then what we see is, we see which is the maximum super pixel value in all the 3 difference images and what is the position of that super pixel. And then we check for all these conditions. The first condition is obvious, is that if there is a flare is happening, we expect the flare intensity to increase over time. Hence we see that the values V1, V2 and V3, which is the maximum superpixel value in the differential image, has to increase over time. Hence V3 has to be greater than V2 and which has to be greater than V1. And for each of them also we've kept a threshold which is not just increased, but each of them also should meet a specific threshold. This will allow us to determine what kind of flares that we want to observe. Like if we want to observe flares starting from C class, then we'll adjust the thresholds based on that. But if we want to limit ourselves to only M and X class flares, then also we can adjust the threshold so that we can decide on what kind of flares we want to capture and what we want to ignore. Once the condition 1 is satisfied, then we have to make sure that these 3 positions where this maximum has occurred, P1, P2, P3, have to be present within one superpixel neighborhood. Like if, so within one pixel neighborhood these positions are present, that is when we say that this is where a flare is happening, and then we localize it. There is one more condition we make sure is whether this position is coming within the solar disk or not, and obviously it is coming outside the solar disk, we will ignore it, calling it a spurious signal. And once we localize the flare, we move on to the region of interest in tracking. It is fairly straightforward. We are not calculating the shift here, rather we have already calculated how the shift happens at different regions on the sun, and we uploaded a lookup table, and we use the values from the lookup table depending on where our current ROI position is, and then use it to understand how much the shift happens. So every half an hour we calculate what is the current region of interest value and how far is it from the sun, and then that corresponding value is looked up in the lookup table to see like if the region of interest is present in this particular part of the sun, how much does it move in a specific time, and that delta x and delta y is retrieved from the lookup table, added to these coordinates, and then our ROI shifts to that particular region and the observation continues. Now the final module is the auto exposure control module. Here we calculate 2 kinds of pixel values. One is the pixels which are bright. We keep a threshold N1 which would be around, it's a 16-bit ADC, so the maximum value is 64,000, which is the pixel saturation value. Hence we keep one threshold which is around 60,000, and one is a lower threshold which is around 30,000. When we see that the number of pixels whose values are more than 60,000 are more than a given number, which means we understand that more pixels are going towards saturation, and hence we have to bring down the exposure time, and that is when the exposure time comes down. And similarly, if we see that if the number of pixels whose values are less than 30,000 are increasing, which means the exposure time is not enough, and because most of the pixels are dark, and that's when we increase the exposure time, and that is how we automatically are able to control the exposure time based on the flare intensity. Now there are some questions which we need to answer in order to make all of this work. The first question is, we have a trigger coming from Solex and Helios, and I've told you that now we move on to the flare localization module. Now if we are able to localize a flare immediately, then it's well and good, we continue. But if we are not able to localize the flare, how long do we want to keep on trying? So that is the first question we need to answer. And next question is, also like I've told you that we want to observe the flare in the initial stages during the rise time. So like how fast is it we have to localize the flare so that we have enough time to observe the initial rise phase of the flare. And how long do you want to observe a flare? And when the auto exposure module is working, we also need to understand like how, to what extent, to what level does the intensity of the flare changes during the flare time, so that we know like what is the kind of exposure times that we need to use in the auto exposure module. So in order to answer these questions, I have done some analysis on using some existing data. So for the soft and hard X-ray, I have used the GOES and the RESI data, while for the soft X-ray, for the NUV, I have used the AIA 1600 data as well as IRIS magnesium data. So what I have done is I have tried to extract some flare parameters like the start times of different flares from hard, soft X-ray and NUV, the peak time, the duration and all these things. And using this we are able to answer some questions and then define how all these algorithms have to work together. So as I said, these are the questions, these are the analysis that I have tried to do using these data, and that has answered these questions. So the first question is, like in some cases I have seen that the hard X-ray or the soft X-ray trigger or the start time could happen as early as 10 minutes before we seeing the flare in NUV. So that is why we have decided that when we get a trigger, once we go into the flare localization module, we will keep on running the module until 10 minutes, and if we don't still observe a flare or localize a flare, we will come back and do the regular operations. And next is the flare detection module. We have seen that in NUV the typical rise time is around 15 to 20 minutes, and hence ideally we would want to localize the flare within this time, and it's better the early we localize it so that we will have enough time to observe the rise phase as well. And the overall duration of the flare in NUV can be anywhere from 45 minutes to up to 2 hours, and we currently fix the flare time to 2 hours. This is the amount of time we were observing the flare, and the amount of intensity that it can increase is around 10 to 15 times. So we have also adjusted the auto exposure in such a way that we can take care of such change in intensities. Last 5 minutes, so I'll quickly show you what is the setup that we have used. I cannot explain the entire setup, but I want to concentrate on this LED that we are using here. So this LED's current is controlled by a current source, and what we have done is, in order to simulate a flare profile, the current that goes to the LED follows a flare profile, so that the light intensity of the LED also follows the profile. As you can see here, this is the light intensity profile of this LED. As you can see, it kind of simulates a flare. So we use this to test our algorithms. So this is the flare localization algorithm. As you can see that this is the full disk image, and this is the LED that is present here, and as in the previous plot, as you can see, the light intensity is increasing. Once it is meeting the thresholds, it is automatically able to understand that the flare is happening, and then define a region of interest around the flare and capture that and observe only that region. For the region of interest, I don't know about the contrast of here, but at least from the table it is we are trying to show is that we have initially fixed the region coordinates to a specific value and then given and ran it for a large amount of time, and to test whether it is automatically shifting to a new region or not, and then calculate and see if it's correctly moving or as well not. In order to test the auto exposure, we have increased the current so that the intensity increases, and check whether the exposure time is decreasing according to the increase in current or not. As you can see here, both of them are the same intensity, but because of the reduction of exposure, you can see here that there are no saturation pixels here. So this now that we know that suit is on board, we have the data coming from suit, so we are able to test our algorithms, we are able to fine tune the thresholds and everything from incoming data. So this plot shows like how we are able to successfully demonstrate the onboard external trigger. So this blue line, I don't know if it's blue or green, but I think you understand what I'm referring to. As you can see, this is the Helios values that are increasing, and this dotted line here shows where we got the Helios trigger. So as you can see, the moment that the trigger count starts increasing, the algorithm immediately kicked in and is able to send a trigger saying that hey, see, there's a probability that a flare might happen. And the moment we got the trigger, this immediately kick-started the flare localization algorithm, and our flare localization algorithm was also able to successfully find the position of the flare and then localize it. Again, I want to stress on the fact that all of this is happening on board without any human intervention. And finally, the onboard exposure control, as you can see that the intensity values are increasing, the exposure time comes down immediately for a step and then again goes back. So with this we are able to demonstrate the successful working of the onboard algorithm on onboard suit, and finally we concluded that it's all working. Thank you.
Thank you.
Before I take the questions, since it's mine is the final presentation, I want to take the opportunity and on behalf of all the participants, thank the ASI and all the responsible people for giving all of us this opportunity. Thanks. Yes, I can take the questions.
So let's take some questions from the audience. Participants.
Hello? Yeah. So thanks for the nice talk.
Thank you.
I have a question regarding the size of the ROI. One thing I want to understand is how does the size of ROI affect the parameters like exposure time, or does it help having smaller ROI compared to a larger ROI? Second, what is the criteria for deciding how big is the ROI?
Yeah, so the ROI affects the exposure thresholds because we are defining like how many pixel values have to be more than a given threshold and how many pixel values have to be less. Hence the size of the ROI determines the threshold, but the good thing here is what is the ROI that we can choose and what are the thresholds that we can keep, all of this can be adjusted. So which means when we want to increase the ROI size, then based on that we can change the threshold numbers in such a way that they will work for a specific ROI. And currently the amount of ROI that we have chosen is 700 pixels and each pixel is 0.7 arc second, so you can count like what is the overall field of view. But since it's a dynamically adjusted thing, for any reason if you come up with a proposal asking for a bigger or smaller ROI, we can change that. And also the cadence depends on the ROI. So if you are choosing a smaller ROI, then we can increase the cadence so that you can get images at a faster rate. So based on this, we are free to choose the size of the ROI.
One more question is, now the disk image is offset. Does it affect any of your algorithms you have developed, or specifically at the edge of the detector?
Yeah. So luckily, even for the flare localization algorithm, we have already expected that it might be a little off. We didn't expect it to be so off, but we expected it to be a little off. Hence, there is an option where we can define the center of the sun with respect to the center of the CCD, and all the algorithms will be based on where the center of the sun is. And hence, even though it is quite off, still we can change the center of the sun so that algorithms can still work. But if it is like completely off and then a small portion of it is cut, then there is nothing we can do.
So this algorithm should also work for off-link flares, and if that happens, you have a separate algorithm for tracking plasma ejections and plasma blobs, which are associated with flares which are happening on the limb, which in principle should have already observed. But you possibly need a higher integration time to be able to get that well. Is that something that...
Yes. I didn't bring that up, but depending on the position of the flare, we have two different flare modes as we call. We call it either a limb flare or a normal flare. So if the flare is happening near the limb, which is the limb with 10% off on either side of the limb, depending on the position of where the flare is happening, we have two different triggers. One, if it's happening around the center, we call it a normal flare, hence the one trigger goes up. If it's happening on the limb, the other trigger goes up. And depending on which flare it is, we decide what filters we want to use, what kind of an exposures we want to use, and all of this can be changed depending on where the flare is happening.
Thanks.
Thank you.
Thanks for the talk, Mohan. I was just wondering, this method that you use to identify flares when this is about to happen and then localize it. So there have been other solar missions also. People must have done this. Is there anything new or novel technique that you used here which wasn't there before? Can you highlight any particular aspect of it?
Yeah,
which is new, altogether new?
that you are able to?
Yeah, I mean, as much as I'm aware of, there is no other solar machine which is together taking the information from its the payloads which are on the same machine, like an hard disk or soft disk payload, and taking the information from its payload which is present around and using the information on board to localize a flare. This is, to my knowledge, is not happening anywhere. There are ones which are detecting the flares from the data that is already there. There are missions which are doing auto exposure and ROA tracking, but this specific way of using the onboard produced hard X-ray and soft X-ray data and using that data to immediately localize a flare in an imager, this specific part is not happening.
So are you saying that the automated onboard flare location is implemented the first time in Aditya? Is that what you're saying?
Yes, using other triggers coming from the other payloads.
In case any background in either soft X-ray detector or hard X-ray, how to reject that?
Yeah, so we have, like as you have seen that, okay, let me go back here.
So background is background event, like some flaring kind of event.
No, you're asking like how do we ignore something coming from?
Flaring kind of event due to background or any custom flare or any other thing.
Okay, so one thing is like, since we have the control on the thresholds that how we are defining something, so if we think that we are getting false triggers, we can go back, look at the data and see how we can change different thresholds and make sure that we are avoiding the false triggers. But in case if that is also failing and for whatever reason we are not able to avoid the false triggers, we can completely cut this line off so that we don't need to take the flare trigger. And here comes another module which again I didn't cover, is a self trigger module, wherein we don't need anything from the external triggers. From the suit data that we are observing already, we can use the suit data and generate a trigger as well. That is what we call a self trigger, which is also there, which is independent of any other payloads that we have on suit.
Any other questions from the audience? I have a final question. So you had in the last slide, you said, thank God it's working. So what was your major worry that it may not work and finally it's worked as expected?
I mean, initially, after we started getting the data, there was a lot of false triggers that were happening for different reasons. Like the moment we are switching on the flare localization trigger, this is one of the things, like we started seeing like triggers coming immediately one after another, and then it's always localizing to a specific point on the CCT. Then we understood like, okay, where the issue was, and we are able to quickly do it. And even the Helios module also was initially not generating triggers, because when we look at the data after we get it, we see that these many flares are happening, but we are not getting those many triggers. So we started seeing these issues, and then but quickly we are able to adjust the thresholds and all these things, and finally like now it is working at an expected efficiency.
So what part of these things go into your thesis, like the after the initial characterization?
Yeah. So my thesis ends at the successful laboratory testing, because the suit data was incoming was after I submitted my thesis. So the final testing on the suit was not part of my thesis. Like the final onboard demonstration is not part of my thesis.
Thank you.
Thank you. Yeah.
So thanks, Manoj.
Thank you.
Let's thank all the speakers, presentations. It was excellent presentations, and so LOC has some.
Since some of the participants are leaving around 1 to 2, so I have asked the caterer to prepare the food by 12. So if you wish, you can avail the food and go.
हाँ सर कर रहा हूँ
Please be present here by 12:50.